Hello everyone, and welcome back to the Natural Gas Engineering Internship at Petro. I hope all of you are doing well. My name is Rahima Babayeva, and I'm a fresh graduate from the University of Aberdeen. I have finished my Master of Science in Petroleum Engineering, and I'm going to be your moderator for today's session on behalf of Arab Oil and Gas Academy. Today's webinar is going to be about natural gas liquids given by Dr. Ahmed Helmi. He graduated his Bachelor of Science in Chemistry Geology in Alexandria University in 1969. His graduate studies included a Master of Science in Chemistry majoring in Analytical Chemistry from South Dakota State University in 1982. Then he pursued his PhD in Petroleum Geochemistry from Alexandria University in 1999. Dr. Helmi joined the oil and gas industry in 1972. He had the opportunity to work as a lab chemist, process engineer, training manager, and he ended his career in the refining industry as a senior manager of laboratories and research at Amrea Petroleum Refinery. He, after retiring from the refining industry, had work experience as consultant chemist for Occidental Petroleum Company in Oman in the steam flooding operation at Mukhaizna oil field. He, after leaving Occidental, has been teaching an adjunct professor of engineering in 3 Egyptian universities. Dr. Ahmed also has trainings with Mobil Oil, Conoco, and American Oil Company in USA. Now, before starting today's session, I would like to mention that you can ask your questions from QA part, and 3 or 5 questions will be answered by Dr. Ahmed Helmi. Let's welcome Dr. Helmi. Dr. Helmi, we are happy to be here today.
Thank you. Hi, everyone. If the screen is okay?
Yes, everything is perfect. You can start. Thank you very much.
This is the title of this lecture, Natural Gas Liquids Recovery. I'll start with this block diagram that leads us to our topic, which is number 6, as a step number 6 in the gas processing, natural gas processing. First of all, we have the gas field where we have gas wells, and from these wells we have the raw gas in the field. We have the separator. From this separator we get the raw gas again after it passed from the separator, and also 2 other phases. The free water will drop down as wastewater or produced water, and we will have the natural gas condensate. This is step 1 in the field. Now, where the raw gas is going to the gas plant. The gas plant could be close to the field or a distance from the field. The second step in the processing of natural gas after extraction from the gas wells, after production from the gas wells, we have the acid gas removal. In this step, we get rid of H2S and CO2, the acid gases, by several processes, as you see it. From step 2, we go to dehydration, where we adjust the moisture content of the natural gas so as not to form hydrates during transportation or during even further processing. We have to get rid of most of the moisture from the gas. It is step 3, dehydration, natural gas dehydration by several processes again. Okay, this is step 3. Step 4, it's the mercury removal. Again, this is a contaminant that should be treated in the gas processing, natural gas processing. In step 4, we have several methods to get rid of mercury in order to avoid corrosion in the if the gas is used as LNG feedstock, or poisoning of the catalyst if it is used in any further processing. Step 5, nitrogen rejection. If the percentage of nitrogen is high, we get rid of most of the nitrogen because it is non-contributing to the heating value of the gas. This is step 5. It could be present and it could not be present. Step 6 is our topic, which is natural gas liquid recovery by several techniques, several technologies that we will cover in this session and tomorrow's session. In this step, we can have the natural gas treated in the previous steps, step 2, 3, 4, 5. We can have, and 6, we can have sales gas as in accordance with the pipeline specs. Okay, we will see these specs very soon. From this step 6, we can have further step. It is the fractionation section, where we can have separate products from the natural gas liquids, which we come out of the natural gas in this 6th step. We can have these products without further treating if the natural gas sulfur content was already very low, so we don't have to invest in step 8. We can have 7 directly go to the final products as you see it: ethane, propane, butane, pentanes plus means C5 plus. So only step 8, which is treating to get rid of sulfur compounds, is necessary only if the gas from the wells had high sulfur content. We will cover on today's session the first beginning of the natural gas liquid recovery process, one by one. Okay, let's go to the next slide. This slide has the sales gas or pipeline gas specifications. And I highlighted the methane concentration and the ethane concentration. The rest, because we are now dealing with step 7, which is step 6, which is natural gas liquids recovery. We are concerned now with the ethane concentration. As you see, the ethane concentration should be in this range, not so you can say 4.6% ethane as maximum, right? Okay. The lower limit is not that important, but the upper limit is the important one, not to exceed 4.6% ethane. As long as you adjust this by processing, you adjust this percentage of ethane, now you can have the rest of the hydrocarbons under control with lower concentrations than this range. You will see this in the next slide. Before we go further, I would like to have a hint about the liquefaction of gases, and we start with the liquefaction of the gases in air. The air composition, as you see, nitrogen, oxygen, carbon dioxide, other gases in very, very small percentage, 1% approximately. And we will see this as technical data, very important before you enter the topic of natural gas liquids or liquefaction. You see this, the oxygen. We only were able to liquefy oxygen in the 1883, in the 19th century. By the end, close to the end of the 19th century, oxygen was liquefied, was turned from gas to liquid, and its boiling point minus 183. Same year, April, we were able to liquefy argon at boiling point minus 186. And as you see, further lower than nitrogen, it came after the argon, and its boiling point, the liquid nitrogen is boiling point is minus 196. In the beginning of the 20th century, 1908, we were able to liquefy helium at minus 269 degrees Celsius. As you see, the harder the liquefaction process, the older, the longer it took to liquefy. This figure, as you see it, 0.00001 Kelvin. This is the closest we were able to get to the zero absolute temperature Kelvin. We were able to get to this figure in 1960, and since then we were not able to get the absolute Kelvin zero. Why? Because at the absolute Kelvin zero, there is no mass. We only have heat in the form of waves, not mass. That's why the absolute zero is impossible. This data is important before you go ahead and study the liquefaction of natural gas or natural gas components. Here we have one more data, technical data, important also. These are the hydrocarbons, starting with methane, ethane, propane, butane, and then the red line means these are the gases or vapors at the room temperature. And as you see, they are all with minus, their boiling point. The liquid form of these gases boil with minus 161 the methane, minus 89 the ethane, minus 44 the propane, minus 0.5 the butane. And this is important. These figures are important in our lecture. Starting from pentane, we have the liquid hydrocarbons boiling at 36, the pentane. So it is a liquid at room temperature. Hexane, heptane, octane, nonane. These form the gasoline range that we use in our cars. Okay. After we cross C9, we have the kerosene. Okay. Then we come to the first slide in our topic, the definition of dry gas and wet gas. I would prefer lean gas and rich gas. We are talking about hydrocarbons, not moisture. With moisture, you can say dry and wet. Dry means no moisture. Wet means there is moisture. With hydrocarbons, it's better to say lean gas and rich gas. Lean gas meaning very low concentration of hydrocarbons that can be liquid at room temperature. This is the simplest definition of lean gas. What about rich gas? You can say it has considerable concentration of hydrocarbons that can be liquids at room temperature. But let us see the definitions in the books. It says lean gas, natural gas that occurs in the absence of condensate or liquid hydrocarbons. Natural gas without liquid hydrocarbons. This is the easiest way to describe lean gas. No liquids can be obtained from this gas. It is the gas that has had condensable hydrocarbons removed. As you see, most of the natural gases can have condensable hydrocarbons. So when there is processing, industrial processing, these condensable hydrocarbons are removed and turn the gas from rich to lean. Again, one more description of lean gas. Dry gas typically has a gas to oil ratio exceeding 100,000 standard cubic feet per stock tank barrel, or the equivalent 2,931 normal cubic meter per stock tank barrel. For every 2,931, almost 3,000, almost 3,000 normal cubic meter, for every 3,000 normal cubic meters produced, you can have 1 barrel only as natural gas condensate, as condensable hydrocarbons. This is the dry or lean gas. What about the wet rich gas? Natural gas that contains less than 85% more methane and more ethane and other heavier hydrocarbons. I would say look at the last statement, the last part of the statement. It says heavier hydrocarbons, natural gas that contains heavier hydrocarbons and more than 85% more, less than 85% more methane. Usually with less than 85% more methane, you will have considerable percentage or concentration of heavier hydrocarbons. Now, look at the numbers, the figures, the data. It simplifies these definitions. The weight gas here, this column is the weight gas, mole percent. As you see, it is 59.52 for the methane, low concentration. But after drying it, the dry gas is 97.17. So we expect this low concentration of methane, relatively low concentration of methane, we expect to have heavier hydrocarbons showing up. But with the methane, 97.17, we expect the heavier hydrocarbons to be in very low concentration, as you see it in this column for dry gas. So this is the wet gas. After processing, it became concentrated in methane to jumped from 59.52 to 97.17, and most of C2 and the heavier were reduced substantially in their percent concentration in the natural gas. So we go from wet gas to dry gas by process that we will show today and tomorrow, inshallah. As you see, there is a frame. I made this frame for natural gas liquids when C2 is targeted. This frame includes C2 as natural gas liquid. So we have a process that's able to liquefy, again, to liquefy ethane among the natural gas liquids, the heavier natural gas liquids. And we have other processes that can only liquefy starting from propane. So there is a process capable of liquefying these heavier hydrocarbons starting from C2, and we have other processes that cannot liquefy ethane, but start with liquefying propane and the rest of the heavier hydrocarbons. So natural gas liquids, when C2 is targeted, is the outside frame, this one, and the natural gas liquids, when C3 is targeted, starting from C3 is targeted, and this is the lower frame. This is the upper frame, and this is the lower frame. Okay, this is important slide to show what we are going to discuss in the next 3 slides. This is the known phase diagram for natural gas. A typical natural gas, as you see, it is a pressure plotted against temperature, pressure versus temperature. And we have this envelope of 2 curves. On the right, the dew point curve, and on the left is the bubble point curve. They are supposed to meet at the critical point On the right of the dew point curve, we have one phase which is vapor, and also we have one phase on the left of the bubble point curve. Up of the upward from the critical point, we have the supercritical fluid region. Very important in the subject of the topic of natural gas liquids recovery is the Cree condenser. This line, this vertical line, which pass through the highest temperature for the gas envelope, the highest temperature that the natural gas envelope can reach. This line, which passes through this point, is called the Cree condenser. It will define what kind of reservoir, gas reservoir, we have in the next 3 slides. Okay, the shape of this natural gas envelope depends on, number one, the concentration. The shape, this shape differs from concentration of its location. Sometimes it's like this. Sometimes it's more further going to the right. It depends on the concentration. And two more important parameters, the pressure and the temperature. So the gas envelope, this gas envelope, the shape of it depends, number one, on the composition, number two, on pressure and temperature. It is characteristic for each natural gas well. For each natural gas well, its gas will have its shape of gas envelope like this. One more important fact about this gas envelope is in between the dew point curve on the right and the bubble point curve on the left, in this area between the two curves, we have two phases. On the right of the dew point curve, we had one phase, is the vapor. On the left of the bubble point curve, we had the liquid phase. Inside the envelope, inside the envelope, we have liquid and vapor, two phases. Okay, this is very important for the coming slides. One more definition. What is the dew point? You can say that the natural gas liquid recovery process, these processes are made to adjust the dew point of the hydrocarbons in the natural gas. What is this dew point? Hydrocarbon dew point, universally used in the natural gas industry as an important quality parameter. It is stipulated it should be written and agreed upon in contractual specifications and enforced throughout the natural gas supply chain. It is compulsory from producers through processing, transmission, and distribution companies to the final end users. Not yet the definition. Here is the definition. The hydrocarbon dew point of a gas is, So it is, I would say from my experience, and I carried out this test in Oman, while in Occidental, I would say the dew point is the first drop you can observe when you, on a cold surface, when the first drop of the gas show up. So when you cool a gas, watch for the first condensate drop. Record the temperature at which this first drop of liquid show up. So it's not seen here the definition, but here this slide talks about the importance of hydrocarbon dew point determination or calculation. The hydrocarbon dew point of a gas is different concept from the water dew point. Again, I said early that we should say wet and dry for moisture, lean and rich for the gas, for the natural gas. Okay, the hydrocarbon dew point of a gas is different concept from water dew point, the latter being the temperature at a given pressure at which water vapor present in a gas mixture will condense out of the gas. So you can say the dew point of hydrocarbons, the temperature of hydrocarbon mixture is the temperature at a given pressure at which liquid hydrocarbon present in the gas will condense out and show up as a liquid. Okay, we are done with this. Natural gas liquids recovery. Most natural gas is processed to remove the heavier than methane hydrocarbons. Starting from ethane, we will have C2. It is expressed as ethane and heavier C2 plus, which are named natural gas liquids. So natural gas liquids in general term means ethane and heavier, starting from ethane and heavier hydrocarbons. Natural gas liquids, it's in more details here. Natural gas liquids include C2, the ethane, C3 propane, C4 butane, natural gasoline C5 plus, and if you start with C6, it is called natural gas condensate C6 plus. So natural gasoline, it means that it is expected to start from C5 and end at C10. Natural gas condensate starts from C6 and it doesn't stop at C9 or C10. It can go to C15 and C16. Okay, purpose of natural gas liquids recovery. Control of dew point of the hydrocarbon components of natural gas to avoid unsafe formation of liquid phase during transportation or in pipelines. So when the natural gas liquids condense during transportation of natural gas, they make problems. Natural gas liquids must be removed for natural gas to meet sales gas specifications. And as I said, it is shown in, it shows up in C2, the ethane percent mole as 4.6 max. Natural gas liquids could be sold as a profitable product. Refiners or petrochemical plants use natural gas liquids as feedstock to their plants. If you extract them from the natural gas, you can sell them to the nearby refiners or petrochemical complexes. Now we will see three different reservoirs according to their natural gas envelope. The first reservoir is dry gas. We are in point one. This is the reservoir pressure and temperature. Here is the correct condenser, the maximum temperature that passed through the envelope. Okay, so the reservoir is here outside. It is higher than temperature, at higher temperature than the condenser, and the separator also is outside the two-phase region, is outside the envelope. So when the gas leaves the reservoir through the well bore of the well and go up to the surface, to the separator at the surface, there is no phase change. It was here as a vapor and ending here in the separator as a vapor. No liquids from this reservoir. It is called dry gas or lean gas. Okay? Okay, let's see the second. This one is condensate retrograde reservoir. The reservoir temperature is in between the condenser and the critical point. So when we see the pressure of the gas drops due to the production, the pressure of the gas drops from 1 and go to 2. This is completely vapor, okay, one phase. But as it goes through the tubing, through the production path, through the tubing, it will condense as it enters the two-phase region inside the envelope. So also, this is the wet gas that we need to rely on, the wet gas reservoir that we want to rely upon when we target to have natural gas liquids from the natural gas. But I think we skipped this one. I'm sorry. We skipped this one. It is the retrograde. Here is number one, point one. The reservoir is in between the critical point and the condenser. So here it in from 1 to 2, it starts to liquefy at point 2. It means in the reservoir. So we don't need condensates inside the reservoir, because it will stop the flow of the gas. So from point 1 to the surface, we will have interrupted gas flow. At times, we will have no gas flow because of the formation of condensate inside the reservoir. This is not desired for targeting natural gas liquids recovery. But this one, we can have this one because there is no condensation inside the reservoir as the hydrocarbons leave the reservoir and go to the surface. It will only drop here in the separator as natural gas liquids, okay? But inside the reservoir, there is only one phase. So this wet gas is the proposed type of reservoirs to produce natural gas liquids. Okay. Natural gas liquid recovery process. Now the process. As you see, we have absorption. We can get the natural gas, the hydrocarbons that can be liquids. We can get them by absorption, by adsorption, by condensation. Okay. This is number one, the lean oil, number one process, the lean oil absorption process. Very simplified flow diagram. This is the feed gas, natural gas, coming in through absorber. This absorber receives lean oil. It can be from the kerosene range to solar gas oil. It could be either kerosene or gas oil. We call it lean oil, okay? This lean oil drops inside this column, the absorber column, all right? This is a column, and it has trays or it has packing. It has either trays or packing. The natural gas going up because it is light, and the lean oil is going down as it is heavier. Counter current, there is contact between the two phases. The heavier hydrocarbons are preferentially absorbed into the oil. This oil comes out from the absorber with the heavier hydrocarbons dissolving in it. And we want now to get rid of these dissolved or absorbed hydrocarbons, because they will be a product for us. So the rich oil, rich in hydrocarbons, will enter a fractionating column that boils off these hydrocarbons, and we will get them here and condense them later as natural gas liquids. What about the natural gas itself after removal of the heavier hydrocarbons with the oil? It comes out from the absorber as dry natural gas. As I said, this is very simplified flow scheme from only two columns. On the left, we have the absorber. On the right, we have the stripper or the fractionating column. We will see more detailed one on the next slide. Here is the more detailed one. This section is the absorption, and this section is the fractionation. In the absorption, we have this absorption tower, but the inlet gas can be, its temperature could be reduced by heat exchange with the outlet gas from the absorber. Here we have a cooler. Why? Because in absorption, the lower the temperature, the more the absorption. the absorbed gases. Okay, so the lowering the temperature is recommended in the absorber. While distillation, in distillation we should have the temperature gets, as the temperature gets higher, we will have more separation. So these are two opposite to each other. That the absorption section needing lower temperature, the fractionation section needing higher temperature. This cooler before the absorber to get the gas to a lower temperature. This cooler could be water cooler, or we can make it chiller. We can have it as a chiller by propane chilling. Okay, by using propane as a chiller. We will study this tomorrow, inshallah. We will have this chiller or the propane refrigeration tomorrow, inshallah. But today we say we can have here a cooler to lower the temperature of the natural gas, so to make the absorption easier into the lean oil. Okay, the heavy hydrocarbons, these are dissolved in the lean oil, which enters the near the top of the column, and then the gas, the dry gas or the lean gas go out. It is cold, so it heat exchange with the inlet gas, and we get the residue gas. One more naming of the sales gas. We have now sales gas, pipeline gas, and also it is called residue gas. Okay, the three are meant for the same thing: residue gas, sales gas, pipeline gas. Okay, it all referred to the final specs of the gas after processing. Okay. Now we have the oil coming out of the absorber, rich in heavy hydrocarbons. It first go to the deethanizer. It is a stripper. It is a fractionating column, but stripper. It will let the C1 and C2 get out of the rich oil. Here we're saying in the absorption, we are saying that the oil will preferentially dissolve or absorb the heavier hydrocarbons, but some light, very low percentage of the light hydrocarbons can also be dissolved inside this absorber because of the high pressure. I said low temperature, and the absorption process need two parameters. The lower the temperature is better, the higher the pressure is better. So the higher pressure does not differentiate between light and heavy. So some of the light will dissolve in the rich oil, and you get rid of them in this column. All right. Now we need the product. The product in this column will be distilled by this fractionating column, and we have the natural gas liquids as the product, and the lean oil comes out from the bottom, cooled, pumped, cooled again, and then enter the absorbers. This oil absorption process is not yet established or constructed in the world. It is old process, and few plants are still working, mostly in the United States and Canada. The new plants do not go to this oil absorption process because it is hard to control its operation. The percent recovery is lower than the newer methods that we'll see on the next slides. Okay, the absorption method again, it's this process description that I just told you about, nothing new, okay, because we are running out of the time. This is the typical liquid recovery levels. C3, as you see, there is no recovery piece for C2 in this process. C3, 80%, C4, 90%, C5 plus, 98%. The other methods that we will study later have higher recoveries than this one. Okay, this is the design criteria, no time to discuss it. Okay, solid absorption in natural gas liquid recovery. We, instead of the oil, we can use solid absorbent that can preferentially absorb the heavier hydrocarbons and leave C1 and C2 as gas. So this is just a vessel, and it is packed with a bed, absorbent bed. And this is another vessel. We should have two vessels, one in process and one in regeneration. The inlet gas go from the top, gets out from the bottom, and here we have sales gas. For sure, it's not as easy as this, but this is a very simplified flow diagram. For the regeneration, as long as this is going on, it is in the cycle process, its cycle is process. The second vessel has its bed in regeneration cycle. Okay, what's going on in the regeneration cycle? Part of this gas go here to compressor and then to the heater. It comes out at 200, at 300, very high temperature. Okay, just why? Because we want to vaporize the heavier hydrocarbons that are absorbed on this. We are going to turn it from liquid form into vapor form. So it goes out and then condense it. Here is separator, and here are the liquids that comes out from the in the regeneration stage. But here we have the inlet gas and sales gas as a product, and here we have natural gas liquids also as a product. Some of the gases are flashed here and will be used as fuel gas. Which solid bed we can use? You can have silica gel, activated charcoal, molecular sieves. Each plant has its selection, its choice, which one can be used. When to regenerate? When the bed becomes saturated with condensates, when the absorbed material breakthrough detected in the outlets. When you reach this saturation with condensates on the adsorbent, you will start to see heavy hydrocarbons going out with the outlet gas. You will see rich gas again, not dry gas. You will see rich gas, not lean gas. Okay, and this could be easily detected by the gas chromatograph. Operational cycle time, what's the time left? What's the time for each, for the cycle? From 20 minutes to 2 hours. How much condensate are present with the natural gas? Preferable recommended cycle 1 hour, but I have here a case study from Rosetta gas plant in Egypt at the Mediterranean coast, and it has, as I read here, process cycle 3 hours. The vessel is big, with large dimensions, and as you see here in details, we have the silica gel they used commercially called sorbate edge material. It is silica gel prepared on purpose to adsorb heavier hydrocarbons. This is from Rosetta gas plant. This is the details. You see here the difference between very simplified flow diagram, and here we have detailed process flow diagram, and it is easier to interpret by this abbreviated form of the main equipment used in the Rosetta plant. The gas filter, adsorption tower or adsorption vessels, filters again, heater, cooler, subcooler, knockout drum. If you see these equipments, you can easily read this process flow diagram. All right. There is regeneration, as I said, the process and regeneration, they are both 3 hours each. Okay. Now we have the production path. We can have a reservoir here, and this is the gas envelope. This is just introduction to tomorrow's lecture. This here is the reservoir, and this is the tubing, and here is the entrance into the surface equipment. This is the gas exchanger, and here we have the chiller to condense the heavier hydrocarbons. This is the first one, mechanical regeneration, represented by ABC. I'm saying this is just introduction to tomorrow's lecture. We have here the reservoir conditions of the wet gas reservoir, and this is the production path from R to A. And from A to B is a gas heat exchanger. It is present on all of the coming processes. From B to C represent the propane chiller. From B to C dash represents the self or JT, Joule Thomson refrigeration, ABC dash. From ABC to dash, the cryogenic refrigeration. So after we are finished with the oil absorption method, then the solid absorption method, we come to the condensation method, from absorption to adsorption to the condensation. The condensation can be done by these three: mechanical refrigeration, sulfur JT refrigeration, cryogenic refrigeration. How they are present in the pressure temperature plot diagram. To show the gas envelope, the natural gas envelope, you see here the reservoir. It is on the right of the condenser, and it is a wet gas reservoir. So the production path will enter below the retrograde condensation zone, and it will enter the gas heat exchanger at point A. At point B is the start of from P to C is the start of the chiller, when the gas goes through the chiller. From B to C dash, when the gas goes through the JT valve. And from B to C dash, when the gas goes through the turbo expander. These three methods will be discussed in tomorrow's session in details. Here is the power consumption in JT valve, 16,000. Turbo expander, 15,799. Mechanical refrigeration, 15,037. Silica gel, 15,218 kilowatt. As you see, this is from Rosetta Gas Company, Rosetta Gas Plant. They show that the silica gel absorption is comparable in power consumption with the three condensation processes, not far from these figures. This is the fractionation processing. After we get the natural gas liquids from the absorption or adsorption or condensation, these natural gas liquids are separated further by consecutive distillation towers. The first one will boil off the ethane, and so the column is called, the distillation column is called deethanizer. The second one will boil off the propane, so it is called the depropanizer. The third one will boil off the butane, and we will get at last the natural gasoline as a natural gas liquid. Okay, the natural gas liquid. But these are ethane. It is liquefied ethane. This one is liquefied propane. And for the butanes, we can further, this is optional, we can also fractionate it into isobutane from the top and normal butane from the bottom. This is called the vapor recovery unit. or the fractionation unit. It is the end of the natural gas liquid processing. Here is natural gas column operating conditions. For each column in the previous slide, you will have here the details, the main design features for our criteria for each column: feed pressure, feed temperature, column operating pressure, overhead product temperature, bottom product temperature, overhead product, bottom product. Very, very, very good data to know about the main parameters in the design of these of this section. This was the last, Dr. Rahima. This was the last slide in my presentation. Dr. Rahima, are you here?
Yes, yes, I am here.
Okay. This was the last slide in my presentation.
That's perfect. Thank you so much for informative session. We are very grateful you took the time out of your busy schedule to address our group. And if you don't mind now, I would like to pursue with the questions of our audience.
Okay, go ahead.
Okay, the first question is, what's the difference between critical point and a bubble point?
Okay, the bubble point, start with the bubble point. The bubble point is the temperature at which the first bubble forms in a liquid. So when you heat a liquid, its temperature will rise. With all the phases you have is only one phase, which is a liquid. At certain temperature, you will start to see a bubble. It means that you will see another phase forming, which is a vapor inside the liquid. You record this temperature as bubble point. The critical point is the temperature above which the two-phase existence for any substance will stop. And there is only, if you go further than the critical temperature, you will only see one phase, which is vapor. Again, below the critical temperature, you can have the condensable substances can have two phases, vapor and liquid. Above this temperature, there is no liquid can exist, only vapor. This is the definition of the gas critical temperature. It means if you increase the gas temperature or the vapor temperature to the critical temperature, above which this vapor cannot be condensed. It will stay as vapor, whatever you increase its pressure. Whatever you increase its pressure and its temperature, it will stay as a vapor. Okay?
Thank you very much. The second question is, how many % of liquids can be extracted from mist extractor in separator, and how many % of liquids are available in rich natural gas when it comes to dehydration column?
Please say the first part. Say the first part of the question first.
Okay, how many % of liquids can be extracted from mist extractor in separator?
No, I can't get it. What he means by separator?
The question is, how many % of liquids can be extracted from mist extractor in separator?
For mist extract in separator?
Yeah. Extractor, yeah.
Extractor and separator?
Yeah, I can go on to another question if the question is not understandable.
I would like to say that
Okay.
how many I would rephrase the question as what is the percentage of natural gas liquids we can extract from a given natural gas, from a given raw gas. It depends on how the method you are using to liquefy the hydrocarbons, the method you use, it depends on the pressure and temperature you can reach in condensing these gases. And every method has efficiency, percent efficiency. There is no method that is 100% efficient with 100% efficiency. This is my answer.
Thank you very much. And the second part is how many percent of liquids are available in rich natural gas when it comes to dehydration column?
Dehydration?
Yeah.
In the dehydration column?
Yeah. How many percent of liquids are available in rich natural gas when it goes to dehydration column?
Okay, I would say the percent liquefiable hydrocarbons in the natural gas, it depends on its original composition before entering the processing plant. So each natural gas well has its own unique composition. We don't control this. It depends on the nature of the reservoir, how the natural gas was formed. Was it formed due to thermogenic through the thermogenic procedure or the biogenic procedure? So the thermogenic procedure can have different composition than the biogenic procedure. Then we will have the gas at the surface. Again, this composition will be affected by how much temperature and the pressure we are using with the gas at the wellhead. This is my answer to the question. Okay.
Thank you very much. And could you please explain supercritical state in phase envelope?
The critical what?
Supercritical state in phase envelope.
In the phase envelope, again, I said when we have the bubble point curve and the dew point curve, they meet at the top of the gas envelope in the point which we call critical point. At this critical point, we still have two phases, the gas phase and the liquid phase. After passing this critical point as pressure, we don't have any more liquid phase. We only have vapor phase. Okay?
Yes, thank you very much. And the final question is, can you please explain about lean oil? What kind of lean oil is used and what are its characteristics?
Okay, I said it before, we can use kerosene as lean oil. It is the oil without hydrocarbons, no hydrocarbons dissolved in it before entering the absorber. We call it lean oil. It can be the kerosene can be used, and also the gas oil can be used.
Thanks a lot for answering our question with a special attention. We hope we shall see you in our next sessions as well.
Thank you
so much. And guys, please do not forget to finish and submit the quiz before deadline. Moreover, you can watch this webinar again from PioPetro's YouTube channel. Stay safe, everyone.